Welcome to Demystifying Math. In this lesson, we're going to be discussing systems of equations that involve three equations and three unknowns. The solutions to these systems of equations will either be that it has no solution or that it has an infinite number of solutions. When you have three equations and three variables, each equation will represent a plane. All three planes could possibly intersect at a single point, which is typically what we're looking for when we're solving a system of equations. I've drawn the three planes here as part of a rectangular solid, but you have to imagine that these are infinite planes. The three planes could possibly intersect at a single line. The three planes could have no intersection, and that means that the three planes are parallel. You could also get no solutions when two planes are possibly intersecting, but not all three planes intersect in even one point. Another choice is when all three planes coincide. If your three planes coincide, that means that the three equations must be equivalent. Take a look at this example. R1 is our first equation, R2 is our second, and R3 is our third equation. If I multiply 3 times the first equation, I get the second equation. If I multiply 5 times the first equation, I get the third. And if I multiply 5/3 by the second equation, I get the third. So there's a relationship between all of these equations. Let's try to use some Gaussian elimination to try to solve this system. If we multiply -3 times the first equation and add it to the second, notice that we get 0 equals 0. It doesn't really help us solve for x, y, or z, but it does give us an idea that there's an infinite number of solutions. If I multiply -5 times the first equation and add it to the third, I also get 0 equals 0. That's telling us that these two equations are coinciding. If the first equation coincides with the second and the third, then the second and the third must also coincide with each other. So in this case, any ordered triple that satisfies the first equation also satisfies the second and the third. So any solution that you get for the first equation will work for all three. And you can get ordered pairs just by plugging in values for two of the variables and solving for the third. If your three planes are parallel, then there is no solution to the system. Let's see what happens with this example. We're going to go ahead and put it on a 3D grapher. Okay, so what I've done is graphed the three equations on a 3D grapher. So you can start to see that these three planes are parallel. And if they're parallel, they're never going to intersect each other. So let's go back and look at this algebraically to see how we can tell whether they are parallel or not. Okay, so we have these three equations, we have our graph, and what we want to do is try to use our Gaussian elimination to solve. So we're going to take row 1, or equation 1, and add it to the negative of the second equation. And when we do that, we get 0 equals -1. This is not a true statement. Like in the last one where they coincided, we got 0 equals 0, which gave us an infinite number of solutions. In this case, what's happening is we have no solution at all. So the first two equations are going to be parallel. Now, even if just two planes are parallel, it really doesn't matter what happens to the third one, whether it intersects the other two planes or not, because there's never going to be a point at which all three planes touch. So that's enough to say that there is no solution to this system of equations. Our other choice when we have an infinite number of solutions is when the three planes all intersect at one line. Let's look at this new set of equations on our 3D grapher. Okay, so here I have all three planes drawn on the 3D grapher. And what you should notice is that they all are intersecting at one particular line. So what we want to do is actually find some points on that line so that we can have some solutions to this system of equations. Okay, so what we want to do is find some ordered triples. So we're going to do that by trying to solve the system of equations first. So using some Gaussian elimination, we're going to multiply the first equation by 2 and add it to the second equation multiplied by -5. And it simplifies down to -3y minus 4z equals 6. Then we're going to replace row 2, or equation 2, with our new equation in our system of equations. Now I'm going to take row 2 and add it to row 3, and notice I get 0 equals 0, which is telling us that there's an infinite number of solutions between those two equations. So that really doesn't help us much to solve for y or z. So what we're going to do is find a relationship between our coordinates so we can get some ordered pairs that satisfy all three equations. We're going to do that by letting z equal a, and then we're going to find x and y in terms of a. So going back to your third equation, which was 3y plus 4z equals -6, we're going to replace z with a and isolate y. So by isolating y, I got -4/3 a minus 2. Now to solve for x in terms of a, we're going to use the first equation where we have 5x minus 4y plus 3z equals 8. And we're going to replace y with the -4/3 a minus 2 and replace z with a. And then again we want to isolate x. So our first step would be to distribute the -4, and we got 16/3 a plus 8. And then I notice that the two 8's are going to cancel out. So we have 5x plus 16/3 a plus 3a equals 0. Then we have two a terms that I combined as 25/3 a. And then I brought the 25/3 over to the other side. And then multiplied by 1/5. So I have that x is equal to -5/3 a. So now I know that my ordered triple is of the form where x is -5/3 a, y is -4/3 a minus 2, and z is a. Now in order to find solutions to the system, all you have to do is plug in any value you want for a. So let's let a equal 3. So that gives us -5, -6, 3. Then I decided to let a equal -3, and I ended up with 5, 2, and -3. Then I let a equal 6, and I have -10, -10, and 6. Now what we're going to do is go back to our 3D grapher and plug in those points to see where they land on our graph. Okay, so looking at the table here, you can see the triples that were plugged in. And if you look on your graph, you'll see dots for each one of those triples, and one is right here. So we have these 3 points here on our graph, and you can see that they line up with that line that all 3 graphs have in common. To algebraically check your work, plug your 3 ordered triples into the original 3 equations and see that you get the correct solutions. Okay, thank you for tuning in to Demystifying Math.